Okay, so this is the second of two pre-recorded lectures for the week that I'll be away. So now we're getting into a new chapter on iterative methods for ax equals b, back to the case where a is assumed to be squared and invertible. So I'm going to spend a few days on this part with iterative methods leading up for iterative methods for symmetric positive definite matrices leading up to the conjugate gradient method. Now, first, since we've been focusing so far only on direct methods like Gaussian elimination, I want to point out some reasons why iterative methods for ax equals b could be a very good idea, or put another way, what's wrong with direct methods. So, for example, if you're about to solve ax equals b and you already have some idea as to the solution, some approximation to x, direct methods like Gaussian elimination have no way to take advantage of that. That they're just built to start from scratch, no matter what other information you may have. Also, what if you only need an approximate x? What if having only 1% error or something like that is perfectly fine? Then there's no way to there's no way to stop early if you and settle for lesser accuracy. You have to go all the way to the end. And that could be wasted effort if if A and B are quite erroneous, then why go for full precision in that case? If a matrix is sparse, as I mentioned earlier, for certain sparse matrices like banded matrices we saw earlier, pivoting can lead to fill-in. It can destroy sparsity. Fill-in is getting non-zero entries outside of a band. So we need some way to deal with the case of sparse matrices, which are very important in a lot of applications. If you don't have A as a traditional two-dimensional array where you have each entry aij, maybe A is represented implicitly as a function, y equals f of x. So the input is x, the vector you want to multiply by. The output is A times x. And representation like that is not conducive to direct methods like Gaussian elimination. So being able to perform matrix vector multiplication with A is enough to solve ax equals b, believe it or not. Okay. Types of iterative methods. Stationary iterative methods that can be described as a fixed point iteration, where you have some initial guess x0. You substitute into some function g to get x1, substitute x1 to get x2. You keep substituting. And the idea is that hopefully this converges to the exact solution. We're not actually covering those in this course. In my other class, Math 561, which will be offered next spring, if you are in the book for section 5.1, we're just skipping over that. So these are some well-known stationary iterative methods. What we're going to focus on in this class are non-stationary. The idea is that from an initial guess, you find some search direction to go in that's meant to get you closer to a solution. And once you've chosen that direction, you perform what's called a line search, and that determines what you multiply that direction vector by to get from one iterative to the next. A subset of non-stationary iterative methods are called Krylov subspace methods, and we'll be spending a lot of time on those, but not today. So what we're going to focus on now are called gradient descent methods. We're just going to look at one method today, and that is the method of steepest descent. And then we'll improve on that later. So, I'm going to use plain old x just to refer to the exact solution. So for non-stationary iterative method, you're taking a step from xk to xk plus 1, your old guess to your new guess, and the step you take is in this direction pk. Pk is called a search direction. Alpha k is some scaling factor that's meant to provide maximum progress towards the exact solution by some criterion. Ideally, we'd like the search direction to be parallel to the error. Of course, we don't know what the error is exactly because we don't know what x is, but we want to try to approximate that as best we can. So we're going to assume for the time being that A is symmetric, positive, definite. And so we can describe the problem of solving ax equals b as in terms of minimizing this function 5x. So we have so this function here, we can use multivariable calculus. To find where a function of several variables has a minimum, you want a gradient to be equal to zero of a zero vector, and you want a Hessian matrix, a matrix of second partial derivatives, to be positive definite for a minimum. So the gradient of this function is ax minus b. Now recall from multivariable calculus that the direction of steepest descent is minus the gradient, so that would be b minus a times whatever x you've plugged in. That is the residual, you may recall, from before. Okay, and then the Hessian of your function phi, in this case, is just a, which is assumed to be symmetric positive definite. So we just have to find out where gradients equal 0, and we will have our minimum, and also our solution, x. So the idea is from whatever iterate we have, xk, we form our steepest descent direction by computing a residual for that xk, and then we describe our new iterate to be of this form. So the only thing left to determine is a parameter alpha k. So our xk plus 1 being of this form, we're going to end up solving a one-dimensional minimization problem to make this value as small as possible. So we can think of this as now being a function only of alpha k, and minimize as in calculus 1, where you take the derivative with respect to alpha k, set it equal to 0. So that's what we'll do here. So I'll define the function g of alpha to be phi with this form for xk plus 1 plugged in, where alpha is unknown. All right, so then we take the derivative, a bit of algebra here, and this is what we get. And then we set it equal to 0. So we get our root. So this is how far we go along that search direction. Keep in mind, because A is symmetric positive definite, this quantity is always strictly positive for a non-zero residual. So we don't have to worry about division by 0. And because about a second derivative test, the second derivative is turns out to be equal to this, as we can see by looking back at our formula. Take a derivative of this with respect to alpha. And again, by A being symmetric positive definite, that is guaranteed to be positive. So this critical point for alpha is a minimum. So now we have the algorithm. So we choose some initial guess. And if you don't know what to choose for the initial guess, you can always just choose the 0 vector. But if you do have something that's in the ballpark, this algorithm lets you take it into account. So we just keep iterating. So for each iterate that we have, xk, we compute the residual. From there, we use this formula to get alpha k. And now we use our alpha k and our search direction to get our new iterate, xk plus 1. At this point, what's not written here, it's implied by the until convergence part here. We need to check whether we have converged to some tolerance. For example, what you could do is look at the norm of xk plus 1 minus xk and see if that's less than some tolerance. And if so, then the loop will end. Now, one problem with the method of steepest descent is if A is ill-conditioned, then what happens is the level curves of your function 5 that you're trying to find a minimum of are these really elongated hyperellipsoids. So if you just take a direction of steepest descent that's given here, you would actually make very little progress towards the minimum. So this method, well, it seems to make sense, and it technically does work. You're guaranteed to make at least some progress towards the solution with every iteration. Progress can be quite slow. It ends up taking very small steps. Okay. So in the ill-conditioned case, it's not very effective. Now, you can also show, and I might have assigned this as a homework problem. I don't recall if I chose this particular one, that each residual, each new residual RK plus 1 is orthogonal to the previous residual RK. And that's all well and good. You want your search directions to be independent of one another. But the problem is, we only know that it's independent of that one. It could, it's not, each new residual is not necessarily independent of previous search directions. So that's what we'd like to have. We'd like to have each search direction independent of all previous search directions, just so we're not covering old ground. What ends up happening, because it's orthogonal to the previous one, but not necessarily others, you could have like a zigzag effect where it keeps trying the same direction over and over again. So that's one trait of a slow convergence that steepest descent has. So in fact, even the 2x2 case, that's where you see it. Because you think of a 2x2 case, 2x2 matrix, whatever iteration should produce a solution very quickly, but that doesn't happen, unfortunately. If A is ill-conditioned, it takes a long time. Okay. At some point, I have some MATLAB code that can demonstrate this for well-conditioned and ill-conditioned case. What I could do is upload that to Canvas. All right. Oh, I've forgotten that I have this in my notes here. Oh, okay. Just explaining why it's the direction of steepest descent. In terms of something you learn about in multivariable calculus, the directional derivative. So how much does the function phi change in the direction of a unit vector u? That's defined to be the dot product of the gradient of phi with u, which is also the magnitude of gradient times cosine theta. This formula would also, for dot product, would also have a magnitude of u in here, but u is a unit vector, so it has magnitude 1. So that's why we don't see that in here. So we want the direction of steepest descent. We want the function phi to decrease. So we want this to be as small as possible. This is fixed regardless of the direction of u. And right here, we have cosine between -1 and 1. So we want cosine to be equal to -1. Now, theta here is the angle between the gradient of phi and u. So in other words, we want u and the gradient to be pointing in opposite directions, to have an angle between them of pi or 180 pi radians or 180 degrees. So that's why the direction of steepest descent is a negative gradient. So this is the decrease that we get. Okay, so I didn't have much today, but what I'm going to do, so next class, when I'll be back, is get into what's called a Lantrell's algorithm, where we'll improve on steepest descent in a way to ensure that each residual is orthogonal to all previous residuals and obtain a more rapidly converging iteration that way. And that's it.